On the morning of June 6, 1944, at precisely 0530 hours, Technical Sergeant Marcus Webb stood on the rain-soaked deck of a Liberty ship 12 kilometers off the Normandy coast, watching the largest armada in human history prepare to change the world. The wind carried the smell of salt water and diesel fuel, mixing with the acrid tang of anxious sweat from 15,000 men packed onto vessels as far as the eye could see. Webb clutched a leather satchel containing technical drawings that his commanding officers had called impractical, foolish, and a waste of precious resources. They had laughed when he first proposed his solution to what military planners had identified as an unsolvable problem that could doom the entire invasion before a single soldier reached the beach. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What none of those officers knew that grey morning was that in less than 6 hours, Marcus Webb's ridiculed innovation would mean the difference between success and catastrophic failure, transforming him from an ignored voice in the shadows to the man who salvaged Operation Overlord when everything hung by the thinnest of threads. Marcus Webb had grown up in the Auburn Avenue district of Atlanta, Georgia, where his father operated a small machine shop that serviced agricultural equipment for farms throughout the region. From the age of 7, young Marcus had spent every afternoon after school in that shop, learning to read the language of metal and motion, understanding how gears transferred power and how tolerances measured in thousandths of an inch meant the difference between machinery that ran for decades and contraptions that seized up within weeks. His father, Samuel Webb, had learned his trade from white machinists who occasionally allowed him to observe their work, never imagining that the quiet black man taking mental notes possessed an intuitive understanding of mechanical systems that exceeded their own. By the time Marcus turned 16, he could disassemble and rebuild any engine that rolled into the shop, often improving upon the original design with modifications that increased efficiency or extended operational life. He devoured technical manuals and engineering textbooks borrowed from the colored library, teaching himself calculus and physics while his classmates struggled with basic algebra. His high school principal, recognizing exceptional talent, had written letters to 15 historically black colleges, hoping to secure a scholarship for the young man whose potential seemed unlimited. Tuskegee Institute had offered him a full scholarship to study mechanical engineering, and Marcus had arrived on campus in the fall of 1936 with $23 in his pocket and a hunger to prove that his mind was every bit as sharp as those of the white engineers whose work he admired from afar. He graduated in 1940 with the highest marks in his class, having designed an improved carburetor system that reduced fuel consumption in agricultural tractors by 17%. 3 companies had expressed interest in his design. None had been willing to hire him. The attack on Pearl Harbor had changed everything. Suddenly, the nation that had denied Marcus Webb opportunities based on the color of his skin desperately needed every capable mind to defeat enemies on 2 fronts. He enlisted in January 1942, expecting to be assigned to a labor battalion or quartermaster unit, the typical fate of black soldiers regardless of their education or abilities. Instead, the colonel reviewing his file had recognized the Tuskegee degree and engineering expertise, assigning him to the Army Corps of Engineers with a rank of technical sergeant. For 2 years, Webb had worked in logistics and planning units, designing improvements to supply systems, calculating load distributions for transport ships, and solving the thousands of small technical problems that arose when moving millions of tons of material across oceans. He worked alongside white officers and enlisted men who ranged from grudgingly respectful to openly hostile, learning to navigate the complex social dynamics that determined whose ideas received consideration and whose were dismissed out of hand. The planning for Operation Overlord had begun in earnest in early 1943, and Webb had been assigned to a specialized team tasked with solving one of the invasion's most vexing technical challenges. The beaches of Normandy offered no natural harbors, where the Allied forces could offload the massive quantities of supplies needed to sustain hundreds of thousands of soldiers pushing inland. Military planners had devised an audacious solution, artificial harbors called Mulberry Harbors, that would be towed across the English Channel and assembled off the French coast, creating protected anchorages where Liberty ships could dock and unload directly onto the beach. The Mulberry concept was brilliant in theory, but staggeringly complex in execution. Each harbour required massive concrete caissons, each weighing 6,000 tons, to be sunk in precise positions to form breakwaters. Steel roadways called whale bridges would connect these floating piers to the shore, rising and falling with the tides while allowing trucks and tanks to drive directly from ships to land. Floating pier heads would accommodate vessels of different sizes, and the entire structure needed to withstand the notorious storms of the English Channel. Webb had been one of 15 engineers assigned to develop solutions for the myriad technical problems that emerged during the Mulberry design process. How do you anchor floating piers in unpredictable currents? How do you prevent the steel bridges from twisting apart in heavy seas? How do you synchronize the sinking of massive caissons to create uniform breakwaters? The white officers leading the team had welcomed his mathematical abilities, assigning him calculations that others found tedious or difficult, but his suggestions for design improvements had been met with polite dismissal or, more often, uncomfortable silence. The most critical problem had emerged during sea trials of the Whale Bridge sections in March 1944. The steel roadway segments, each 29 meters long and designed to link together while floating on pontoons, had demonstrated a catastrophic flaw. Under the weight of heavy vehicles, the bridges exhibited a wave-like motion that intensified as successive vehicles crossed, creating a resonance effect that threatened to tear the connections apart. Engineers called it harmonic oscillation, and it meant that the bridges would fail precisely when they were needed most, when columns of trucks and tanks attempted to move rapidly from ship to shore. The design team had tried 17 different solutions over 2 months. They reinforced the connection points with heavier steel, added damping mechanisms to absorb the motion, modified the pontoon spacing to change the resonant frequency. Nothing worked. The wave motion persisted, and in one particularly disastrous test, a fully loaded supply truck had been thrown into the sea when a bridge section buckled under the accumulated stress. The driver had survived, but the message was clear. The Mulberry harbours, upon which the entire invasion's logistics depended, had a fundamental flaw that no one could solve. Colonel Harrison Blackwell, the project's commanding officer, had called an emergency meeting on April 14th. 22 engineers, officers from the Corps of Engineers, Navy construction battalions, and civilian contractors crowded into a conference room in Portsmouth, staring at technical drawings and test reports that documented their collective failure. Blackwell, a West Point graduate with 12 years of experience in military construction, had made his frustration abundantly clear. The colonel said, his voice tight with stress, "We have 47 days until D-Day. We have invested millions of dollars and thousands of man-hours in these harbors. Without them, we cannot sustain the invasion force beyond the first week. But if these bridges tear themselves apart every time a deuce and a half drives across, we might as well have built nothing at all. I need solutions, gentlemen. I need them now." The engineers had proposed modifications to existing designs, each suggestion a variation on approaches that had already failed. Heavier materials, different connection angles, additional support structures, all addressing symptoms rather than the fundamental problem. Webb had sat in the back of the room, listening to each proposal and mentally calculating why it would fail, seeing the flaw in the reasoning before the speaker finished explaining the concept. Captain Robert Sinclair, a structural engineer from Boston, had suggested adding crossbeams between the pontoons to reduce lateral movement. Webb had immediately recognized that this would increase drag in the current, creating additional stress that would worsen the oscillation. He had raised his hand, waiting for recognition that never came. Major Thomas Henshaw, who had designed bridges for the Tennessee Valley Authority before the conflict, proposed changing the road surface material to something more flexible, allowing the bridge to absorb the wave motion rather than transmit it. Webb saw the flaw instantly. A flexible surface would create unpredictable traction for vehicles, especially in wet conditions, and would likely develop cracks that would compromise the structural integrity. After 90 minutes of circular discussion, Colonel Blackwell had dismissed the meeting. instructing everyone to return with workable proposals within 72 hours. As the room emptied, Webb had approached the colonel, satchel in hand, intending to present the solution he had developed over the previous 3 weeks. Blackwell had been gathering papers, clearly exhausted and frustrated. "Sir," Webb had begun, "I believe I have identified the source of the harmonic oscillation and developed a solution that addresses the root cause rather than the symptoms." The colonel had looked up, his expression shifting from distraction to something harder to read when he registered who was speaking. Blackwell was not overtly prejudiced like some officers Webb had encountered, but he carried the unconscious assumptions of his era and upbringing. He had never dismissed Webb with overt hostility, but neither had he ever seemed to truly see him as an equal to the white engineers on the team. "Sergeant Webb," Blackwell had said, his tone carefully neutral, "I appreciate your enthusiasm, but we have our best minds working on this problem. I am sure your calculations have been helpful to the team, but bridge design at this level requires specialized expertise." Webb had persisted, opening his satchel to remove the detailed drawings and calculations he had prepared. "Sir, with respect, I have that expertise. I studied structural mechanics at Tuskegee under Professor William Patterson, who trained at MIT. I have reviewed all the test data, and I believe the problem is not the bridge sections themselves, but the timing of how vehicles cross them." Blackwell had glanced at the papers without really seeing them. "The timing," he had repeated, skepticism evident in his voice. "Sergeant, we have tried spacing the vehicles differently. It does not solve the oscillation problem." "Not spacing, sir," Webb had explained, his words coming faster as he sensed the colonel's attention slipping away. "Active dampening through synchronized counterweights. The oscillation occurs because each vehicle's weight creates a downward force at regular intervals, and these forces synchronize with the bridge's natural frequency. But if we attach weighted pendulums beneath each pontoon, calibrated to swing in opposition to the wave motion, they will absorb the energy instead of allowing it to build up." The colonel had paused, actually looking at Webb's face for the first time in the conversation. "Pendulums," he had said flatly. "You want to hang pendulums under a floating bridge?" "Yes, sir," Webb had continued, encouraged by even this small engagement. "The mathematics are straightforward. The period of oscillation for the bridge under load is approximately 2.3 seconds based on the test data. A pendulum with a length of 1.32 meters will have the same period but in opposite phase. When the bridge rises, the pendulum swings down. When the bridge falls, the pendulum swings up. The opposing forces cancel out, damping the oscillation before it can build to dangerous levels." Blackwell had set down his papers, and for a moment, Webb had thought he might actually consider the proposal. Then the colonel had shaken his head, a small smile playing at the corners of his mouth, the kind of smile an adult might give a child who had suggested something charmingly naive. "Sergeant Webb," the colonel had said, his tone now almost gentle, "I commend your initiative, but you are describing a textbook physics experiment, not a practical engineering solution. We are talking about bridges that must support 20-ton tanks in storm conditions while floating on one of the most unpredictable bodies of water in the world. Adding hundreds of pendulums would create maintenance nightmares, increase the weight we need to tow across the channel, and introduce countless new failure points. The idea, while creative, is simply not practical for field conditions." Other officers had remained in the room, gathering their own papers and materials, and several had overheard the exchange. Captain Sinclair had chuckled, not unkindly, saying to a colleague in a voice just loud enough to carry, "Give the man credit for trying. At least he is thinking about the problem, even if the solution belongs in a classroom rather than a combat zone." Webb had felt the familiar burn of dismissal, the particular humiliation of having his work judged not on its merits, but on assumptions about who he was and what he could possibly know. He had encountered this throughout his education and career, the reflexive skepticism that greeted any assertion of expertise from someone who looked like him. Sometimes it came wrapped in polite words about practicality or experience. Sometimes it was more direct, but it always carried the same underlying message: your ideas, no matter how sound, do not merit serious consideration. He had gathered his papers and left the room without another word, returning to his desk in the shared office where junior engineers worked on routine calculations and paperwork. For 3 days, he refined his design, running the numbers again and again, checking for flaws in his reasoning, testing his assumptions against the physical realities of storm conditions and combat operations. The mathematics held. The physics was sound. The engineering was elegant in its simplicity. On April 17th, he had submitted a formal written proposal through proper channels, a 12-page technical document with detailed drawings, mathematical proofs, and a step-by-step implementation plan that could be executed in less than 2 weeks. The proposal had gone to Major Henshaw, who supervised the junior engineering staff. Webb had checked daily for a response, but none came. His design had disappeared into the military bureaucracy, buried under more urgent matters, or perhaps simply ignored. The engineers had continued searching for solutions to the Whale Bridge problem. They had tested modified connection systems, experimented with different pontoon configurations, and even considered abandoning the steel roadways in favor of less efficient but more stable alternatives. Nothing worked well enough to guarantee success under combat conditions. As D-Day approached and the massive invasion fleet began assembling, the Mulberry Harbors remained a critical vulnerability in the plan. On May 22nd, just 15 days before the invasion, a final full-scale test had been conducted in the protected waters off Portland. A complete Whale Bridge section, 244 meters long, had been assembled with the latest modifications. A convoy of 12 heavy trucks had been scheduled to cross at normal convoy spacing, simulating the urgent supply movements that would occur once the invasion began. Webb had not been invited to observe the test. He learned about the results the following day, when the entire engineering team had been summoned to an emergency briefing. Colonel Blackwell had stood before them, his face grey with exhaustion and worry, and delivered the news that everyone had feared. The bridge had failed catastrophically. The wave motion had begun with the third truck, building rapidly as each successive vehicle added its weight at precisely the wrong moment. By the time the 8th truck reached the midpoint of the bridge, the oscillations had grown so severe that the connection points had begun to fail. The 9th truck had been thrown sideways as a bridge section twisted free from its moorings, and only quick action by the driver had prevented the vehicle from going into the water. The test had been halted immediately, with the convoy retreating to shore and the bridge structure showing stress fractures at 17 separate connection points. Blackwell had explained, his voice hollow, that they had 2 weeks to solve the problem or admit that the Mulberry Harbors could not perform their intended function. The invasion would proceed regardless. That decision had been made at the highest levels, but without reliable harbors, the logistics situation would be catastrophic. Supplies would have to be offloaded onto smaller landing craft and ferried to shore, a process that would reduce delivery capacity by 70% and leave the invasion force desperately short of ammunition, food, fuel, and medical supplies within days. The colonel had assigned around-the-clock shifts, dividing the engineering team into groups that would work on different approaches simultaneously. Webb had been assigned to a calculation group tasked with stress analysis. Important work, but far from the creative problem-solving happening in other teams. He had accepted the assignment without comment, recognizing that his earlier proposal had marked him as someone who did not understand the boundaries of practical engineering. But he had not stopped thinking about the problem. At night, in the small quarters he shared with 3 other non-commissioned officers, he had refined his pendulum design, working through scenarios that the original proposal had not fully addressed. What if the storm conditions were worse than anticipated? What if the pendulums themselves began to resonate? What if the added weight affected the bridge's buoyancy in unexpected ways? For each potential problem, he had developed solutions. Adjustable pendulum lengths to account for different load conditions, friction dampers to prevent unwanted resonance in the pendulum systems themselves, hollow pendulum weights filled with seawater to add mass without significantly impacting the overall weight budget. The design evolved from a simple physics demonstration into a robust engineering system that could function under the chaotic conditions of military operations. He had drafted a second proposal, even more detailed than the first, and on May 28th, just 9 days before D-Day, he had hand-delivered it to Colonel Blackwell's office. The colonel's aide, a young lieutenant named Morrison, had accepted the document with barely concealed impatience. "Sir, Webb had said to the lieutenant. "I need to speak with Colonel Blackwell directly. This proposal could solve the Whale Bridge problem." Morrison had glanced at the cover page, seeing Webb's name and rank. "Sergeant," he had said, "the Colonel is dealing with about 5,000 urgent matters right now. I will make sure he sees this, but I cannot promise when that will be. We have less than 10 days until the largest military operation in history, and everyone seems to think their particular issue deserves the Colonel's immediate attention." The document had joined a stack of papers on Morrison's desk, and Webb had left the office knowing that it would likely never reach Blackwell's hands. The military hierarchy had many virtues, but responding quickly to unsolicited proposals from junior enlisted men was not among them. The final days before the invasion had passed in a blur of frantic activity. The engineering team had settled on a compromise solution for the Whale bridges, reinforcing the connection points with additional bracing and limiting the weight of vehicles that could cross simultaneously. It was not elegant, and it would slow the flow of supplies significantly, but it was the best they could do with the time remaining. The Mulberry Harbour components had been loaded onto towing vessels, and the massive fleet had begun moving toward the assembly points off the English coast. Webb had been assigned to the construction crew that would travel with the Mulberry components, helping to assemble the harbours once the invasion secured the beaches. He would be aboard the Liberty ship SS Samuel Chase, along with 200 other engineers, construction workers, and Navy specialists who would turn the floating puzzle pieces into functional harbours while under potential fire from the German defensive positions that still held portions of the coastline. Now, standing on the deck as dawn broke over the Armada, Webb watched the coast of France emerge from the morning mist. The sound of distant explosions reached them across the water, the bombardment that preceded the landings, and he could see the flashes of artillery fire illuminating the grey sky. Thousands of landing craft were moving toward the beaches, carrying the infantry that would establish the foothold for everything that followed. Next to him at the rail stood Chief Petty Officer Daniel Kowalski, a Navy construction specialist from Chicago who had worked on bridge projects for the Corps of Engineers before the conflict. Kowalski had been one of the few white servicemen who had treated Webb as a professional equal rather than an oddity or a problem, and the two had developed a working friendship based on mutual respect for each other's technical knowledge. Kowalski said, gesturing toward the coast where tiny figures could now be seen scrambling up the beaches, "Those boys are buying us the opportunity to do our job. We better make sure the harbours work, or they will be trapped here with no way to bring in what they need to push inland." Webb nodded, thinking about the whale bridges packed into the holds below them, each one a potential failure point that could cripple the entire supply operation. He had tried. He had proposed a solution that he knew would work. But the military was not structured to listen to ideas from people like him, and now thousands of lives might pay the price for that institutional blindness. The Samuel Chase held position 12 kilometers offshore throughout the morning, waiting for the signal that the beaches were secure enough to begin the harbour construction. Radio reports filtered through the ship, fragmentary and often contradictory, describing fierce resistance at some beaches and rapid advances at others. By noon, the situation had stabilized sufficiently for the construction phase to begin. The first Mulberry components to be positioned were the massive concrete caissons that would form the outer breakwater. These enormous structures, called Phoenix caissons, had been towed from British ports by ocean-going tugs, and now they needed to be sunk in precise positions to create a protective barrier against the waves and currents. Webb watched from the deck as the first caisson was maneuvered into position 600 meters offshore from a beach designated as Mulberry A Engineers. Aboard small launches used rangefinders and compass bearings to ensure the placement was exact. Then valves were opened to flood the hollow interior chambers. The massive concrete box settled into the water, sinking gradually until it rested on the seabed, with just the top 5 meters visible above the waterline. The process was repeated again and again, each caisson positioned exactly 60 meters from the next, creating a curved breakwater that would eventually span nearly 2 kilometers. It was an extraordinary feat of engineering and coordination, made more remarkable by the fact that it was happening while sporadic fire from German positions still swept across portions of the beach. By late afternoon, the breakwater was complete, and attention turned to the floating pier sections that would allow ships to offload directly onto the bridges. These pierheads, massive steel structures riding on multiple pontoons, needed to be anchored within the protected harbour area and connected to the shore-spanning whale bridges. The first pierhead was positioned successfully, its anchors set in the seafloor and its surface deck rising and falling gently with the tide exactly as designed. Now came the critical moment. The first whale bridge section needed to be connected to the pierhead and extended toward the shore. Webb joined the work crew, along with 40 other engineers and construction workers, boarding small landing craft that ferried them to the floating construction site. The steel bridge section, its roadway surface wide enough for 2 trucks to pass, rose and fell on the gentle swells, its pontoon supports keeping it level and stable. Senior Chief Warrant Officer Patrick Riley, a Boston native with 15 years of Navy construction experience, supervised the connection process. The bridge section had to be precisely aligned with the pier head, then secured with heavy-duty pins that locked it into position while still allowing the slight motion needed to accommodate tidal changes. Riley barked orders to work crews on both structures, using hand signals when the wind made verbal communication impossible. The connection was made successfully, and Riley ordered a test vehicle to be brought forward. A jeep, the lightest vehicle that would use the bridges, drove carefully from the pier head onto the bridge section, its weight causing the pontoons to settle slightly deeper into the water. The bridge remained stable, with no significant motion. Riley nodded approval and ordered the jeep to drive the full length of the section, 244 meters, to the point where the next section would be attached. The jeep completed its run without incident, and Riley signaled for a heavier vehicle. A 2.5-ton truck, what the soldiers called a deuce-and-a-half, rolled onto the bridge. The pontoons settled more noticeably under the greater weight, but the structure held firm. The truck drove to the end and back, generating small waves in its wake, but no problematic motion in the bridge itself. Riley said to his assembled crew, looking better than the test results from Portland, "Maybe those reinforced connections are working. Let us keep building." Additional bridge sections were brought forward and connected, extending the roadway from the pier head toward the beach. By sunset, 3 sections were in place, creating a 732-meter bridge that ended about 100 meters from shore. The final section, which would include an adjustable ramp to accommodate different tide levels, would be positioned the following morning. As darkness fell, Webb and the other construction workers returned to the Samuel Chase for food and rest. The day had been exhausting, but successful. The Mulberry Harbor was taking shape, and if the weather held, they would complete the assembly within 3 days. Supply ships could then begin the critical work of offloading the materials that would keep the invasion force advancing inland. Webb fell asleep in his bunk, still wearing his work clothes, too tired to change, his mind running through calculations for the following day's tasks. He slept dreamlessly for 4 hours, then woke to the sound of raised voices and running feet on the deck above. Something was wrong. He climbed to the deck and found chaos. The weather had shifted dramatically. Winds that had been light and variable during the day had intensified into a gale blowing from the northeast at over 45 kilometers per hour. The sea, which had been relatively calm, now ran with waves over 2 meters high. Rain fell in sheets, reducing visibility to a few hundred meters, but the weather alone was not what had prompted the emergency. The whale bridges were failing. Webb could see the lights of the partially completed harbor through the storm, and even from this distance, he could observe the violent motion affecting the bridge sections. The harmonic oscillation that had plagued the Portland tests had returned with catastrophic intensity. The combination of wind, waves, and the resonant motion of the floating structure had created a perfect storm of destructive forces. The bridge sections were rising and falling in great waves, each motion more extreme than the last, the steel roadways flexing and twisting in ways they were never designed to accommodate. Colonel Blackwell stood on the deck with a group of officers, watching through binoculars as their carefully constructed harbor began to tear itself apart. A Navy launch approached the Samuel Chase, bringing Major Henshaw from the harbor site with an emergency report. The Major climbed aboard, his face grim and his uniform soaked through. Henshaw saluted Blackwell and delivered his assessment without preamble. "Sir, we are losing structural integrity across all 3 bridge sections." The reinforced connections are holding for now, but the stress is exceeding design limits. We have already observed cracks forming in 2 connection points, and if this continues, we will have complete failures within hours. The entire harbor will be unusable. Blackwell lowered his binoculars, his expression a mixture of frustration and resignation. "Can we disconnect the bridges and wait out the storm?" he asked, "then reconnect when conditions improve?" Henshaw shook his head. "Sir, disconnecting under these conditions would be extremely dangerous, likely to cause the very failures we are trying to prevent. And even if we succeed, reconnection would take another full day, putting us significantly behind schedule. The invasion force is already running low on certain supplies. We cannot afford that kind of delay." Blackwell was silent for a long moment, staring out at the failing harbor. "Then what do you recommend, Major?" Henshaw spread his hands in a gesture of helplessness. "Sir, I do not have a good recommendation. We can attempt emergency reinforcement, sending crews out to add additional bracing, but in these sea conditions, that would risk lives for questionable benefit. We can wait and hope the structures hold until the storm passes. Or we can accept that the Mulberry Harbor concept has failed and fall back to the original plan of using landing craft for supply delivery, which will create a logistics nightmare, but at least is a known quantity." The officers began discussing the options, their voices rising to be heard over the wind. Webb stood apart from the group, forgotten in the crisis, his mind racing through calculations. The storm conditions had created exactly the scenario his pendulum system was designed to address. The wind was adding irregular forcing to the wave motion, but the fundamental problem remained the same. The bridges were oscillating at their natural frequency, and the motion was building to destructive levels because nothing was damping the energy. He moved closer to the group of officers, waiting for a break in the conversation. When none came, he simply spoke, his voice cutting through the discussion. "Sirs, I have a solution." The officers turned to look at him, several with annoyance at the interruption, others with confusion about who this enlisted man thought he was to inject himself into command discussions. Colonel Blackwell recognized him after a moment, his expression shifting to something like pity. "Sergeant Webb," the colonel said, "this is not the time for theoretical proposals. We are facing a real crisis that requires immediate practical action." Webb held his ground, pulling his satchel from where it hung at his side. "Sir, I submitted a proposal 4 weeks ago for a pendulum damping system that would prevent exactly this type of harmonic oscillation. The mathematics showed it would work then, and the mathematics show it will work now. With your permission, I can stop the bridge motion within 10 minutes of implementation." The claim was so audacious that it created a moment of stunned silence. Captain Sinclair, who had chuckled at Webb's earlier proposal, now laughed outright, the sound harsh and bitter in the wind. 10 minutes, he repeated. "Sergeant, we have been working on this problem for months. You think you can solve it in 10 minutes with some pendulums hung from string?" Webb looked directly at Sinclair, his voice steady and certain. "Not string, sir. Steel cables with adjustable weights. And yes, 10 minutes to demonstrate the concept at small scale, perhaps 30 minutes to implement across all bridge sections, depending on available materials and crew size." Major Henshaw, to his credit, appeared genuinely curious rather than dismissive. "Explain it," he said to Webb. Webb opened his satchel, removing the detailed drawings he had carried since that first rejected proposal. The wind tried to tear the papers from his hands, but he held them firm, using a cargo crate as an improvised table. The officers gathered around, some skeptical, others simply desperate enough to consider any option. "The problem," Webb began, speaking quickly but clearly, "is that the bridge has a natural resonance frequency, determined by its mass, length, and the resistance of the water. When waves hit the pontoons, or when weight loads the surface at regular intervals, it creates forcing at or near that natural frequency. Without damping, the motion builds with each cycle until structural failure occurs." He pointed to the first drawing, which showed a cross-section of a pontoon with a pendulum suspended beneath it. "The solution is to add pendulums calibrated to have the same period as the bridge's oscillation, but oscillating in opposite phase. When the bridge rises, the pendulum weight swings downward, pulling the pontoon back down. When the bridge falls, the pendulum weight swings upward, checking the downward motion. The result is active damping that prevents the oscillation from building. Blackwell studied the drawing, his engineering training evident in the questions he asked. How do you calibrate the pendulum length correctly? How do you prevent the pendulums from creating their own resonance problems? How do you implement this quickly enough to save the bridges tonight? Webb had answers prepared for each question, refined through weeks of solitary work on a proposal that no one had wanted to seriously consider. The pendulum length is calculated from the period formula, approximately 1.32 meters for a 2.3-second oscillation period. We can adjust it in the field by observing the bridge motion and trimming the cable length. The pendulums themselves are damped by drag through the water, which prevents runaway oscillation in the weights, and implementation requires only steel cable, weights, and a way to attach them to the underside of the pontoons. He pulled out additional drawings showing the attachment mechanism he had designed, a simple bracket that could be bolted to existing pontoon structures without requiring welding or major modification. The weights could be anything dense and readily available: sandbags, ammunition crates, even lengths of anchor chain. The key was getting the mass and length correct. Henshaw looked at Blackwell, his skepticism visibly warring with the desperate need for any viable solution. "Sir," he said, "the theoretical basis seems sound. I studied harmonic motion at Virginia Tech, and this is textbook physics, but implementing it under these conditions, in the dark, in a storm, and expecting it to work the first time, that is asking a lot." Blackwell turned to Webb, and for the first time the colonel seemed to be truly seeing him, recognizing that the man before him might actually possess expertise equal to or exceeding that of the officers he commanded. "Sergeant Webb," he said, "if we try your solution and it fails, we have lost critical time and possibly damaged the structures further. If we do nothing, the bridges will likely fail anyway. Are you absolutely certain this will work?" Webb met the colonel's gaze without flinching. "Sir," he said, "I am as certain of this as I am of anything in engineering. The physics is proven. The only question is execution. Give me a crew, the materials I need, and 30 minutes, and I will save your harbor." Blackwell made his decision. "Major Henshaw," he ordered, "gather every piece of steel cable we have aboard this ship. Find weights that can be attached. Get me a crew of 6 men who can work in rough water, and get them ready to go in 5 minutes. He turned back to Webb. "Sergeant, you just talked yourself into the most important test of your life. I hope to God you are right about this." The next 20 minutes became a controlled chaos of preparation. Webb sketched detailed instructions for the crew, specifying exactly where each pendulum needed to be positioned and how to calculate the correct cable length. Chief Kowalski volunteered for the crew, along with 5 other construction specialists who had experience working on the pontoons. They loaded a launch with steel cable, wrenches, bolt sets, and 45-kilogram weights normally used for anchor systems. The launch fought through the choppy water to the nearest bridge section, which was exhibiting the most severe oscillation. Webb and his crew climbed onto the bucking structure, securing themselves with safety lines while waves washed across the roadway. The motion was even more violent than it had appeared from the Samuel chase, the bridge rising and falling through a vertical distance of over 3 meters with each oscillation, the steel surface flexing visibly under the stress. Webb moved to the first pontoon, studying the structure while his mind calculated exact placement for the pendulum bracket. The pontoons were large hollow cylinders, 3 meters in diameter, with attachment points every half-meter along their length. He selected a position at the geometric center of the pontoon, where the leverage would be greatest. He said to Kowalski, fighting to be heard over the wind, "We need to attach the bracket here, with the cable hanging straight down when the pontoon is level. The weight needs to be 1.32 meters below the waterline when at rest." Kowalski and 2 other crew members worked to bolt the bracket in place, while Webb prepared the cable and weight assembly. The physical labor was made brutally difficult by the constant motion, each tool threatening to slip from wet hands, each bolt requiring multiple attempts to thread. But these were skilled men accustomed to building under adverse conditions, and they worked with the focused intensity of people who understood that lives depended on their success. The first pendulum was ready after 12 minutes. Webb made final adjustments to the cable length, using a measuring tape and adjusting for the current position of the pontoon in its oscillation cycle. When he was satisfied, They lowered the weight into the water, the cable playing out until the weight hung at precisely the calculated depth. The effect was not immediately obvious. The bridge continued its violent motion, the waves unabated. But Webb watched with the trained eye of an engineer who understood resonance systems, and he could see what others might miss. The amplitude of the oscillation had stopped growing. The bridge was still moving severely, but the motion was no longer building toward the catastrophic failure that had seemed inevitable minutes before. Kowalski noticed it too, his experienced eye recognizing the change. "It is stabilizing," he said, wonder evident in his voice despite the wind and spray. Son of a gun. It is actually stabilizing. Webb allowed himself a brief moment of satisfaction, then barked orders to the crew. "The next 5 pontoons," he said. "Same configuration, as fast as we can work. We need complete coverage of this bridge section. Then we move to the other 2 sections." The crew split into 2 teams, working simultaneously on adjacent pontoons. The process went faster as they refined their technique, learning how to work with the motion rather than fighting against it, timing their efforts to the rhythm of the oscillations. The 2nd and 3rd pendulums were installed in 8 minutes each, the 4th and 5th in 6 minutes. By the time the 6th pendulum was in place, the change in the bridge's behavior was unmistakable. The violent oscillations that had threatened to tear the structure apart had been replaced by a gentle rising and falling that matched the natural motion of the sea. The bridge still moved. It was a floating structure, and some motion was inevitable, but the destructive resonance had been eliminated. The stress cracks that had been forming at the connection points were no longer propagating. The structure was stable. From the deck of the Samuel Chase, Colonel Blackwell watched through binoculars as the first bridge section visibly settled into a less violent motion pattern. He lowered the glasses, looking at Major Henshaw with an expression that mixed relief with something approaching awe. Henshaw said softly, "It is working. That crazy pendulum idea is actually working." Blackwell nodded slowly, then turned to Lieutenant Morrison. "Get word to the other construction ships," he ordered. "We need steel cable, brackets, and weights distributed to every crew working on the Mulberry harbors. Sergeant Webb's damping system is to be implemented on every whale bridge section, starting immediately." And Morrison, his voice took on an edge, "When this crisis is over, I want to see every proposal that was submitted regarding the bridge problem. I want to know why Sergeant Webb's solution was not given serious consideration weeks ago when it could have been implemented under controlled conditions." The installation of pendulum dampers continued through the night. Additional crews were dispatched from other ships, working under Webb's direction to outfit all the completed bridge sections with the system. By dawn, 14 bridge sections across both Mulberry harbors had been equipped with the dampers. The storm, which had threatened to destroy the entire harbor system, had instead validated Webb's engineering in the most dramatic possible demonstration. As the wind began to ease with the coming of daylight, the bridges stood firm, their gentle motion damped and controlled, ready to bear the critical burden of supplying an army. The first supply convoy rolled across the whale bridges at 07:15 on June 7th, 5 loaded trucks moving in close succession, their combined weight creating the exact conditions that had caused failure in previous tests. The bridges flexed slightly under the load, but showed no tendency toward the destructive oscillation that had plagued earlier designs. The convoy completed its crossing without incident, and within the hour, a steady stream of vehicles was moving from ships to shore, carrying ammunition, fuel, food, and medical supplies to the soldiers pushing inland. Webb stood on the beach, exhausted from 36 hours without sleep, watching the bridges that had been saved by an idea that had been laughed at and dismissed. Chief Kowalski approached, carrying 2 mugs of coffee he had somehow procured from a quartermaster unit. Kowalski handed one mug to Webb and raised the other in a toast. "To the man who saved the invasion," he said. "You proved every one of those doubting bastards wrong." Webb sipped the bitter coffee, feeling the warmth spread through his cold and tired body. He did not feel triumphant exactly. The success of his system had vindicated his engineering, but it had also highlighted the institutional failures that had nearly led to disaster. How many other good ideas had been dismissed or ignored because they came from the wrong person? How much harder had this conflict been made by the systematic exclusion of capable minds based on arbitrary characteristics that had nothing to do with competence or intelligence? Colonel Blackwell found Webb later that morning, as supply operations were reaching full efficiency. The colonel looked as exhausted as Webb felt, but there was a new quality in the way he looked at the younger man, a recognition that had been absent in their previous interactions. "Sergeant Webb," Blackwell began, then paused, seeming to struggle with what to say next. "I owe you an apology. Multiple apologies, in fact. I dismissed your proposal without giving it proper consideration. I allowed my preconceptions about who could possess certain kinds of expertise to cloud my professional judgment. If you had not persisted, if you had not had the courage to speak up again during the crisis, we would have lost the harbors and quite possibly compromised the entire invasion. I was wrong, and I am sorry." Webb was not sure how to respond to such an unexpected admission. Few officers of his experience had ever apologized to him for anything, and certainly not for the kind of systematic dismissal he had faced throughout his military service. "Thank you, sir," he managed to say. "I appreciate that." Blackwell continued, "And I have also recommended you for immediate promotion to warrant officer and submitted a commendation for your service that will go in your permanent record. More importantly, I am reassigning you to the lead engineering team for all future harbor construction projects. From this point forward, your input will be welcomed and seriously considered. You have earned that, and far more." The promotion and commendation were gratifying, Webb supposed, though they seemed small compensation for the weeks of being ignored and dismissed. But the opportunity to contribute meaningfully to future projects, to have his expertise recognized and utilized, that represented real change. It was not justice exactly, but it was progress. The Mulberry Harbors operated for the next 5 months, delivering millions of tons of supplies that kept the Allied armies advancing through France and into Germany. The pendulum damping system became standard equipment on all floating bridge sections, proving its value in multiple storms and rough sea conditions. Other engineers studied Webb's design and proposed refinements, but the basic concept remained unchanged because it worked exactly as the mathematics predicted it would. Webb continued to serve with the Engineering Corps through the end of the conflict in Europe, participating in the construction of bridges, roads, and supply facilities across France, Belgium, and Germany. He worked alongside officers and enlisted men who had learned that competence came in many colors, and that good ideas deserved consideration regardless of their source. Not everyone learned that lesson. The prejudices of an era could not be erased by a single dramatic demonstration, but enough people changed their thinking to make a meaningful difference in how Webb was treated and utilized. After the conflict ended, Webb returned to the United States with a chest full of medals, a resume full of significant engineering accomplishments, and the hope that the nation he had served might extend to all its citizens the opportunities he had fought to defend. The hope was not fully realized in his lifetime. The America of 1945 was not ready to dismantle the structures of racial oppression that limited opportunities for millions of its people. But the cracks in those structures had widened, and men like Marcus Webb had proven beyond any doubt that talent and intelligence were not distributed according to skin color. Webb enrolled at MIT on the GI Bill in 1946, one of the first black students admitted to the graduate engineering program. He completed his master's degree in mechanical engineering while working part-time for a defense contractor that, faced with the choice between missing out on government contracts or hiring capable engineers, regardless of race, chose capability. He designed suspension systems for military vehicles, improved cargo handling equipment for Navy ships, and developed manufacturing processes that increased production efficiency while reducing costs. In 1951, he married Dorothy Henderson, a teacher from Boston whom he met at a lecture on educational equity. They raised 3 children, all of whom attended college and pursued professional careers that would have been largely closed to their father's generation. Webb taught evening classes at Boston University, sharing his knowledge with a new generation of engineers and making sure that students who looked like him knew that they belonged in the field. He retired in 1979 after a 33-year career that had taken him from the machine shop in Atlanta to the cutting edge of engineering practice. He had 17 patents to his name, had mentored dozens of younger engineers, and had proven through his life's work that excellence recognized no racial boundaries. In retirement, he volunteered with programs that encouraged minority students to pursue careers in science and engineering, sharing his story as both inspiration and warning. Inspiration because it demonstrated what was possible with talent, determination, and persistence. Warning because it showed how much potential had been wasted by a society that refused to recognize excellence when it came in an unexpected package. When documentary filmmakers interviewed him in 1987 for a project about the engineering of D-Day, Webb was asked what he thought about when he remembered that stormy night in June 1944. He was quiet for a long moment, his eyes distant as he recalled the scene, the violent motion of the bridges, the desperate rush to prove his concept would work, the satisfaction of seeing the mathematics translate into physical reality. Finally, he said to the interviewer, "I think about all the other people like me who had good ideas that were never implemented because no one would listen. How many lives could have been saved if someone had listened earlier? How much suffering could have been prevented? My idea worked, and I am grateful for that. But I also know that for every time persistence and competence finally broke through the barriers, there were hundreds of times when good ideas died because the person who had them was not seen as someone who could possibly know better than the established experts. That is what I think about. All that wasted potential, all those lost opportunities, all the progress we could have made if we had judged ideas on their merits instead of judging people on their appearance." The story of Marcus Webb and the pendulum dampers became a case study in engineering schools, taught as an example of elegant problem-solving and the importance of considering unconventional approaches. But it was also taught in leadership and management courses, used to illustrate the costs of institutional bias and the value of creating systems that welcome input from all sources. The fact that Webb's solution had been initially rejected, not on technical grounds but due to unconscious assumptions about who possessed expertise, provided a clear lesson about how organizations could fail even when filled with intelligent and well-intentioned people. In the broader context of World War II history, the Mulberry Harbors represented a triumph of engineering and logistics that enabled the liberation of Western Europe. The artificial ports delivered 2.5 million men, 500,000 vehicles, and 4 million tons of supplies between June and November 1944, making them one of the most successful engineering projects of the entire conflict. The pendulum damping system that saved the harbors during the critical early storm was a footnote in most histories, a technical detail that only specialists knew about. But for the engineers who studied the project, for the historians who understood how close the invasion came to logistical failure, and for the descendants of men like Marcus Webb, who continued to fight against the barriers that limited human potential based on arbitrary characteristics, the story carried profound significance. It demonstrated that innovation could come from anywhere. That expertise was not the exclusive province of those who looked or sounded a certain way, and that organizations that welcomed diverse perspectives were more likely to succeed than those that limited input to a narrow elite. The broader struggle for civil rights and equality continued long after Webb's moment of vindication on that stormy June night. The integration of the armed forces, the civil rights movement, the ongoing efforts to dismantle systemic barriers to opportunity, these were not solved by a single engineer's successful design. But each individual success, each moment when competence was recognized and rewarded regardless of the package it came in, added to the accumulating weight of evidence that the old systems of exclusion were not just morally wrong, but practically foolish. Marcus Webb lived to see enormous changes in American society, though he never claimed that the work was finished. He died in 1996 at the age of 77, surrounded by family members whose opportunities he had helped create through his example and advocacy. His funeral was attended by over 400 people, including several former students who had gone on to distinguished engineering careers, colleagues from his decades in industry, and a few very old veterans who remembered him from the engineering corps. Colonel Harrison Blackwell, 91 years old and confined to a wheelchair, was helped into the church by his grandson. After the formal service, the colonel asked to say a few words, and the family graciously agreed. Blackwell spoke slowly, his voice still carrying authority despite his age. He said to the assembled mourners, "I worked with hundreds of engineers during my career in the Army, and in civilian life afterward. Marcus Webb was among the finest I ever knew, and I am ashamed that I did not recognize that fact immediately. He had to prove himself under the most difficult conditions imaginable, facing obstacles that had nothing to do with his competence and everything to do with the prejudices of the society we lived in. He overcame those obstacles through brilliance, persistence, and a generosity of spirit that refused to become bitter despite every justification for bitterness. I learned more from Marcus Webb about leadership, about engineering, and about the cost of prejudice than from all my years at West Point and in command positions. I am grateful that I eventually learned to listen to him, and I regret deeply all the times I did not listen when I should have. He made me a better officer and a better man, and I will miss him. The pendulum dampers that Marcus Webb designed in 1944 continued to be used in floating bridge construction for decades after the war. The principle was adapted for other applications, from offshore oil platforms to floating buildings in earthquake-prone regions. Engineers working on these projects often did not know the origin of the damping system they were implementing, but it did not matter. Good engineering stands on its own merits, independent of who created it. In 2003, the American Society of Civil Engineers established the Marcus Webb Award for Engineering Innovation, given annually to recognize elegant solutions to complex problems that demonstrate both technical excellence and creative thinking. The award citation specifically mentions Webb's pendulum dampers and the circumstances under which they were developed, ensuring that future generations of engineers would know the story. The broader lessons of Marcus Webb's story remained relevant long after the specific technical problem he solved became a historical footnote. How do organizations identify and utilize talent when it appears in unexpected forms? How do institutions overcome ingrained biases that limit their own effectiveness? How do individuals persist in the face of systematic dismissal while maintaining the integrity and generosity that allow for eventual reconciliation? These were not questions with simple answers, and the progress made since 1944 was neither linear nor complete. But each generation that studied Webb's story, that learned how close competence came to being permanently ignored, added to the collective understanding that organizations succeeded by welcoming capability wherever it appeared and failed by limiting opportunity to those who fit narrow expectations. The physical artifacts of Webb's achievement have mostly disappeared. The Mulberry Harbors were designed as temporary structures, and most of the components were scrapped or left to rust after the conflict ended. A few concrete caissons still sit on the seabed off the Normandy coast, visited occasionally by divers who study the marine ecosystems that have colonized them. The pendulum dampers, made of steel cable and weights, corroded away decades ago, leaving no physical evidence of their critical role. But the impact of Webb's work extended far beyond the physical structures. The success of the Mulberry Harbors helped ensure that the invasion of Normandy succeeded, that Western Europe was liberated, that the global conflict that had claimed tens of millions of lives finally ended. The pendulum dampers played a small but crucial role in that success, and the story of how they came to exist illustrated both the best and worst of human institutions. At their best, military organizations and other large institutions could recognize merit, adapt to new information, and incorporate innovations regardless of their source. Colonel Blackwell's decision to trust Webb's design during the crisis, Major Henshaw's willingness to consider an unconventional solution, and the rapid implementation across the entire harbor system demonstrated organizational flexibility and openness to evidence. At their worst, those same institutions could systematically exclude capable people, dismiss good ideas without serious consideration, and allow prejudices to override professional judgment. The weeks that Webb spent being ignored, the laughter that greeted his initial proposal, and the institutional resistance to taking him seriously represented failures that could have had catastrophic consequences. The fact that Webb's persistence finally broke through the resistance was fortunate, but it was also a reminder of how many times persistence failed, how many good ideas were lost, how much talent was wasted because the barriers were too high or the individuals too exhausted from fighting them. For every Marcus Webb whose competence was eventually recognized, how many others gave up after being dismissed once too often? For every innovation that finally got implemented despite institutional resistance, how many died in file drawers or wastebaskets because they came from sources that were not deemed credible? These uncomfortable questions did not diminish Webb's achievement, but they provided context for understanding its significance. His success was personal, a vindication of his skills and persistence, but it was also illustrative of larger patterns, a case study in how organizations could do better, and how much they stood to lose when they did not. In the decades after World War II, the United States slowly and painfully began addressing the systematic exclusions that had limited opportunity for African Americans and other marginalized groups. The integration of schools, the civil rights legislation of the 1960s, the affirmative action programs designed to compensate for historical discrimination all represented efforts to ensure that talent was recognized and utilized regardless of race. Progress was real but incomplete, opposed at every step by those who benefited from the old systems or who genuinely believed that the existing order represented natural hierarchies rather than socially constructed barriers. Marcus Webb's story became part of the evidence marshaled by those who argued for change. Here was a man who had been systematically underestimated and dismissed, whose expertise had been doubted for reasons that had nothing to do with his actual capabilities. And yet, when given the opportunity to prove himself under crisis conditions, he had delivered exactly what he promised, solving a problem that more credentialed engineers had failed to solve. If organizations wanted to succeed, if they wanted access to the best ideas and most capable people, they needed to look beyond the narrow categories that had traditionally defined expertise and leadership. The lesson was not that traditional credentials and experience were worthless. Webb himself had benefited from his Tuskegee education and his years of practical experience in his father's machine shop. Rather, the lesson was that credentials and experience came in many forms, and that organizations that defined legitimate expertise too narrowly were handicapping themselves. A brilliant mechanic who learned his trade outside formal institutions might have insights that a credentialed engineer missed. A woman whose mathematical abilities had been dismissed as unfeminine might solve problems that stumped all male teams. An immigrant whose accent marked them as foreign might bring perspectives shaped by different educational traditions and cultural contexts. Diversity, in other words, was not just a matter of fairness or moral principle, though those were important. It was also a practical advantage, a way of ensuring that organizations had access to the widest possible range of capabilities and insights. The teams that welcomed input from unusual sources were more likely to find innovative solutions than teams that limited participation to those who fit traditional profiles. Marcus Webb understood this intuitively, drawing on his own experience of being underestimated and his observations of how institutions worked. In his later years, when he spoke to students or gave interviews, he emphasized the importance of creating environments where good ideas could emerge from anywhere. He talked about the responsibility of leaders to actively seek out perspectives they might not naturally encounter, to question their own assumptions about who possessed expertise, and to create systems that judged proposals on their merits rather than on the characteristics of their proponents. He also talked about the responsibility of individuals to persist, even when institutions failed to recognize them. Persistence alone was not sufficient. Structural barriers needed to be dismantled and not just climbed over by exceptional individuals. But in the absence of perfect systems, individuals still had to make choices about how to respond to dismissal and exclusion. Webb had chosen to keep refining his proposal, to look for opportunities to present it again, and to maintain his confidence in the soundness of his engineering even when others doubted. Those choices had made the difference between his idea being implemented and it being lost to history. The balance between individual persistence and institutional reform was delicate and often uncomfortable to discuss. Emphasizing persistence could seem to place the burden on those who were already disadvantaged, suggesting that they just needed to try harder to overcome barriers that should not exist in the first place. But emphasizing only structural reform could deny agency to individuals, suggesting they were helpless victims rather than people capable of strategic action and resistance. Webb navigated this tension by acknowledging both realities. Yes, Institutions needed to change, needed to actively dismantle the barriers that excluded capable people based on irrelevant characteristics. And yes, individuals could and should persist, should maintain their confidence in their own abilities, even when others doubted, should look for cracks in the walls and opportunities to prove themselves. Both were necessary, and neither was sufficient alone. The specific story of the pendulum dampers and the Mulberry Harbors was a moment in time, a crisis that was resolved through a combination of good engineering, institutional flexibility, and individual persistence. But the broader themes it illustrated remained relevant across decades and contexts. How do we identify and nurture talent? How do we create organizations that welcome diverse perspectives? How do we balance the need for credentialing and expertise with openness to unconventional approaches? How do we ensure that good ideas get serious consideration regardless of their source? These questions did not have simple answers, and the solutions that worked in one context might not transfer directly to others. But the example of Marcus Webb provided guidance. Listen to people who have demonstrated competence, even if they do not fit your preconceptions about what an expert looks like. Judge proposals on their technical merits before considering the characteristics of the person making them. Create systems that encourage input from diverse sources rather than limiting participation to narrow elites. Recognize that innovation often comes from the margins, from people who see problems differently because their experience has been different. And when you are wrong, when you have dismissed a good idea or underestimated a capable person, have the courage to admit it and change course. Colonel Blackwell's apology to Webb was meaningful, not just because it acknowledged a personal failing, but because it demonstrated a willingness to learn and adapt. Organizations that could admit mistakes and incorporate new information were more effective than organizations that defended their initial judgments regardless of evidence. The engineering principles that Webb applied to the pendulum dampers, understanding resonance, calculating damping factors, predicting system behavior under stress, had direct parallels to the social dynamics of organizations. Just as physical systems could be understood through careful analysis and mathematical modeling, social systems could be understood through observation, reflection, and willingness to test assumptions against reality. Both required humility, the recognition that initial models might be incomplete or wrong, and both benefited from diverse inputs that challenged conventional wisdom. In the end, Marcus Webb's legacy extended far beyond the specific technical contribution he made to the Mulberry Harbors. He demonstrated that excellence had no color, that good ideas deserved consideration regardless of their source, and that organizations that embraced these principles were more effective than those that did not. He showed that persistence in the face of dismissal could pay off, but also that institutions had a responsibility to make persistence less necessary by creating systems that welcomed competence in all its forms. The 10 minutes that it took to demonstrate his pendulum dampers in action, the moment when skepticism turned to acceptance and a dismissed idea became the solution that saved the invasion, represented a turning point not just in that specific crisis, but in broader conversations about who possessed expertise and whose ideas mattered. The ripples from that moment spread across decades, influencing how engineering was taught, how organizations thought about diversity and inclusion, and how individuals understood their own potential, regardless of the barriers they faced. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.